In this video, we're going to discuss the units of radiation. One of the most difficult parts about discussing radiation is relating an amount of radiation to an effect. There's a large number of units that have been created to help do this, but part of the problem is different types of radiation affect things differently. So if we think about, say, the number of decay events, we tend to think of units like the Curie or the Becquerel. The Curie is equal to 3.7 times 10 to the 10 decays per second. This was based on the amount of decays that a gram of radon would produce when they were being experimented with. This is a rather large number most of the time. Many things don't decay that quickly, and so the Becquerel was another unit, which is just one decay event per second. The problem with discussing the number of events is it depends on what type: alpha, beta, beta plus, gamma, some mix. Different forms of decays will result in different amounts of energy being released. So receiving 1,000,000 becquerel from one source is going to do a completely different amount of damage to something than 1,000,000 becquerel from another. In terms of practical use for the safety, counting the number of events isn't necessarily all that useful. We need to differentiate by what those events do to the person or to the object. And so we also have units that try to adjust for this, adjust for the alpha, the beta, the gamma, and relate it to energy. For this we have units. There's the gray. 1 gray is equal to 1 joule per kilogram of biological matter, of tissue. This tends to be a little large, so a lot of times we also use the rad. That's just 1/100th, like centimeter versus meter. And so we can scale it down slightly. This was an effort to convert all the different types of radiation into how much energy is being released by that source, in order to then say, well, this much energy is being bombarded upon a person who's nearby or an animal, and this is the energy they're receiving from that type of radiation. However, even this has its issues because, well, different organisms respond differently to different types of radiation and amounts. A multicellular organism has a protective outer layer of hair and skin, where a microorganism really doesn't have a protective outer layer. A bacteria has only one cell. So things that wouldn't meaningfully harm humans for that same relative amount of energy per kilogram could be far more destructive to smaller organisms, even scaled for their size differences. And so the energy alone also isn't really enough to let us know just how much damage we're really receiving from something. And so there are adjusted calculations. Basically the amount of energy adjusted by what organism, how they're exposed. Is it external or is it internal? A radiation source that's outside your body versus one that's been ingested does very different amounts of damage. Ingested one can get right up near critical organs, and even inside them if it's water soluble, where an outside source has to pass through all your material. And so the type of exposure, the nature of the biological organism, the cells, all this can factor in. The short version is there's a multiplying factor that adjusts for that biological material and that situation and how it's exposed. And so we have our adjusted dosages. These are the Rem and the Sievert. Loosely assuming an adjustment value of 1 Rem is going to be equal to 1 rad. The Sievert, 0.01 sieverts, is equal to 1 rem. Now in reality, our adjustment factor is often not 1, but to a loose approximation, and in some cases it is. The energy can fully be absorbed. How does this affect things? What is the amount of absorbed radiation that's safe or harmful? Well, in general, about 5 to 20 rem. If you were to be exposed, spread out over your whole body in an acute radiation event, so a burst of radiation, if you absorbed about this much rem, this has the risks of long-term possible consequences. But if you're in the 20 to 100 REM exposure, this has notable consequences. Reduction in white blood cells, so this can reduce your white blood cell count. Basically, the damage was done spread out, and any fast-dividing cells tend to die because some of their DNA was damaged, and if they didn't get a chance to repair it, when they go to divide, they'll destroy themselves instead. And so your fast-dividing cells tend to take a hit here. If you're up around 100 to 200, you have radiation sickness. Vomiting, diarrhea, various other ill effects. Our gastrointestinal tract is oddly more susceptible to radiation than some of our other cells, and so we tend to respond fairly quickly in forms of intestinal distress as our radiation level starts to rise. By the time you're at 500 rem, this is the LD50 for humans. Approximately half of all humans who receive this level in an acute dose will not survive. Well, this is short-term exposure. Now, this is another problem with radiation. How much you receive in what amount of time also affects how dangerous it is. A lot of radiation in a short amount of time is extremely dangerous. A low level of radiation over a long period of time is actually something we deal with constantly. In fact, you are bombarded by cosmic rays all the time, receiving several millirem per year. The rocks beneath our feet contain various radioactive materials, potassiums, trace uraniums, and the like. They're always decaying and exposing us a little bit. When you eat a banana, since it's high in potassium, you get more potassium inside and increase your exposures. Potassium ions float freely through the blood, get used in various parts of our cells, and can cause internal damage. There's nothing we can do about that. We need those ions, and our body's built to handle it to a degree. We can simply absorb some damage and repair it. But as your dosage increases over time, it strains your systems. You have to work harder to constantly repair, and things can slip past. So the background radiation, well, it's always there. If it's at elevated levels, it can have long-term health effects, where a short-term spike of radiation can have short-term and long-term health effects. All this makes discussing the amount of radiation persistently difficult. Let's try and relate some exposure to this. In the previous video, we calculated out the average decays of 1 mole of uranium per second over its first half-life. What we found was that for uranium-235, there was approximately 14 million decays per second. This was based on a 700 million year half-life. If we had 1 mole of uranium, so half of it went away, on average over that half-life, this was the number of decays per second. Let's take a look at that in terms of the amount of radiation. We need to know the energy of a single decay, and for uranium-235, that is approximately 3.2 times 10 to the minus 11 joules per decay. That's its average decay energy. Various differences can occur, but that is the average energy of a single decay of uranium-235. So using this, we can convert this to the rads. I have 14 million decays per second, and I know that in every 1 decay, there's 3.2 times 10 to the minus 11 joules for 0.000448 joules per second. Well, that would be in grays. Our rads are 1/100th of that. So there's 0.01 joules in every 1 rad. So this would be 0.0448 rads per second, or 45 millirads per second. Well, assuming a biological conversion of 1-to-1 again, this means that's approximately 45 millirem per second. Let's round up a little here, 0.05 rem per second. And we said it was about 5 rem before you started running into possible later effects. Well, that would only require us to be near this for 100 seconds. So if you were to absorb all the radiation being given off by a mole of uranium-235 decaying for 100 seconds, which pretty much just looks like it sits there, no noticeable weight is going to disappear, you'd have enough damage to start taking long-term health effects. Make it 1,000 seconds, so hanging out for a good part of an hour near something you didn't realize was on the table next to you. And now you're up into the radiation sickness zone. Remember, uranium's density is 19 grams per milliliter. You only need 235 grams here to be a mole. So you're talking something 13-ish cubic millimeters. Tiny little block that you didn't realize was out. One little uranium rod. There's a reason why a lot of workers in early nuclear plants had issues with exposure. There's some fairly famous movies about people being exposed during uranium processing in the early days, people trying to cover it up. But if you're near it and you're being exposed to it reasonably throughout the day, you're very quickly going to accumulate a very dangerous amount of radiation. Now, is that reasonable that you're absorbing all of it? No. If you've got, say, a source of radiation here and it starts emitting it, and you have a person hanging out over here, well, there's some amount of radiation that's going to hit them. But as distance goes on, that radiation spreads out farther. The further away you are from the source, the less of those radiation events will hit you. But the closer you get in, the more of the events overlap the person. Proximity to the source greatly increases your exposure. This ends up following an inverse squares law. So very quickly as you get away, there's significantly less radiation being exposed. If you've ever played Fallout, you may have noticed this. As you walk near a source, your counter spikes incredibly. So calculating out just how much radiation you're going to get is also dependent on your distance from the source, how open your source is. And one more complicating factor here for uranium is that if you actually have a concentrated source of uranium, it starts producing cascade reactions. Uranium goes through chain reactions where one decay can cause multiple other decays. It actually decays faster if it's concentrated, at least for uranium-235, which is why we use it for things like bombs. It can sustain a chain reaction, elevating this rate at which uranium decays to the point where you can destroy almost all of it in a nuclear explosion. And so while the diffuse rate of decay was calculated at 14 million per second, a concentrated source would actually be different and vastly higher. So we can see some units and we can do some calculations. I hope to impart to you just how difficult it is to truly relate a lot of this. Without a great deal of preparation, knowledge of the system, knowledge of the source and the recipient, it's very difficult to readily express just how much radiation is really going on and how much damage that radiation is causing. This is why our medical devices are very, very carefully designed. The radiation sources and the devices used are very heavily engineered to deliver only a set amount in a set way, so we can be very certain about what is happening.